two categories. Okay. I'm going to start off by talking about two categories directly by exploring an analogy between two physical phenomena: encrypted communication, which is a classical phenomenon in classical computation, and quantum teleportation. So first of all, we're going to look at encrypted communication. So often in computer science, physics, many subjects, we might draw heuristic diagrams to model the sort of thought process we have, the way we think about the system. This is such a heuristic diagram. This is no formal meaning. It's just something we draw on the back of an envelope to help us understand what's going on. So why would we draw this picture to represent encrypted communication? So what happens in encrypted communication? Well, we start with some message, some plain text we want to transmit. We know we're doing cryptography when we start pretending that words that are really two words are one word. So we have plain text and ciphertext, like that. So we have this message we want to transmit. We've got some images, of course, and then we share a secret key with a partner, somewhere else. We met our partner in the past, performed this key exchange procedure locally, and then we went our separate ways. Crucially, those keys, those two copies of the keys have got certain properties that make them useful. They're private. Not anyone can read this key. The copies we've got we keep in our pocket, or encrypted on our hard disk or something. And also they're perfectly correlated. Right? May as well just say they're identical strings. That's not represented in this picture, but it's just something we understand. Okay, so the next phase of this encryption procedure, inputs encryption procedure, this plain text message, and this secret key. Something happens, a classical computation, and as the result there is some ciphertext. So in the simplest case, this plain text is an a length n string of bits, and the secret key is also a length n string of bits, just a random string. Then the encryption procedure is the bitwise exclusive OR of the message and the secret key. And you can show this tells you absolutely nothing about the original message, because every single bit of the message has either been flipped or not at random, depending on the corresponding bit and the secret key. So when we get our ciphertext, this contains no information at all about the plain text, so we can broadcast it freely. We don't need to worry about letting people get access to this ciphertext. And so we treat this broadcast information in a very different way. So I'm drawing it in a very different way. I'm drawing these multiple blue lines to indicate that we're throwing it out in a liberal fashion. It's not localized in space like our secret information is. It's delocalized in space. And then the last thing that happens is that the partner who has access to this second copy of the key also gets access to this broadcasted information and performs a decryption procedure which makes use of both pieces of information. And the result of that will be some output, that will be the decrypted message. So that's how we understand encrypted communications, how we might explain it to a friend who hasn't heard about it. We might draw a little picture like this, an informal picture to help us understand. Now let's draw a picture of quantum teleportation. Looks very similar. Picture's identical, in fact. We've just got slightly different interpretations to the different parts of the picture. So what's going on here? We start with an initial quantum system, and then this stage, a maximally entangled pair of systems is created. The first one of those systems is measured along with our initial quantum system. This measurement will have some classical result, and classical information is quite unlike quantum information. We can certainly broadcast it. So again, we've got two different types of information here: the classical information and quantum information. Just as on the left we have private information and public information. So we broadcast this measurement result. Our partner gets access to that measurement result. Depending on that measurement result, does something to this second member of the entangled pair. And as a result, we can show that this if it's all been performed correctly, the state of this initial quantum system will be transferred to the final system. Totally amazing procedure, obviously impossible in some sense, right? Because all you're doing is transferring classical information from left to right. As a result, the quantum state is transferred. So I'm sure people here, if most of you have got a background in information, are familiar with that. But it's really worth dwelling on the fact that there's a really, really close structural similarity between these processes. interesting fact, one can go on, digging deeper into the sort of into the analogies between these things. This is something people have written about before. There are papers exploring the analogy between classical encrypted communication and quantum teleportation. An interesting fact is that in both of these worlds we have similar foundational debate, which is actually ongoing in both worlds. So on the left-hand side, this encryption procedure is carried out presumably by a classical computer. It's obviously a non-invertible function, so it's an exclusive OR, right? 2 bits come in, 1 bit come out, 1 bit comes out, the exclusive OR of the initial algorithm. But hang on, this classical computer is described presumably by the laws of classical physics. Classical physics is fundamentally time reversible. So how on earth is it possible for a classical computer to ever compute a logically non-invertible function? Right? So we'll scratch your head on that one for a while, but this is the foundations of computation are well developed. So the idea is that whenever your computer computes a non-invertible function, it can only do that by invertible means. So what it does is it pushes some entropy out into the environment. In other words, it creates heat. And the only fundamental bound on the amount of energy that your computer has to use to perform an operation is the Landauer's bound, which says that the amount of heat you use is just proportional to the amount of information that you want to delete as your computation proceeds. You want to push that out as entropy. So it's sort of interesting, and there are debates going on as to whether Landauer's boundary holds. So really understanding, is this fundamentally non-invertible? Probably not. It is described fundamentally by an invertible procedure. How do we understand that? How does that relate to the fact that logically it is non-invertible? We make sure it's the right properties and so on. Very much an ongoing area of debate the foundations of computation. Now what about the right-hand side? Well, it's orders of magnitude worse, right? What is this measurement procedure? Is it a non-invertible procedure? Well, of course it must be, because the wave function is collapsing. Right? We're measuring some pair of quantum systems, we're getting some classical data out. Drastically non-invertible procedure. But of course there are huge ongoing debates in the foundations of computation. Many people would say that this measurement procedure, this is just some physical process that's happening in the world. All of our fundamental laws of physics just say some unitary operator takes place. So how on earth could it be that anything we do, measurement or otherwise, is not correct? And people talk at great length about how you can reconcile this and so on. So not only are these 2 pictures here, encrypted communication, quantum teleportation, structurally similar, that similarity really goes deep, really goes a long way, even down into the question of foundational philosophical difficulties. Okay. Now the main idea of this talk, although because I'm going to make it very didactic and go slowly, we won't really be able to prove this, but the main idea of this research program is that this analogy can be made precise. And the way we make it precise is by using a higher dimensional form of categorical quantum mechanics. And by higher dimensional, I mean a form that makes use of higher categorical. So, now we're going to talk about
Jamie,
Yes?
what's essential about your analogy is that the key is, of course, quantum data.
On the left, it certainly is, yes.
Yeah, but
Sorry, on the right. Yes. Right, so here, this entangled pair is representing an entangled pair of quantum systems. On the left, the secret key is a perfectly correlated pair of private classical systems.
does that mean all keys we know can be copied?
So, I mean, the point is that this key creation procedure is not deterministic. If it was a deterministic procedure, it would be no good, because we assume that our adversary knows the sort of rules of espionage that we're working with. Right? We assume that our adversary has gone to the same spy training college as us. He knows all this sort of stuff we're doing there. So it's no good if our key is deterministic. Right? Our key has to be non-deterministic. So this key creation procedure has to be non-deterministic. And that cannot be covered. Probability distribution cannot be covered. Okay, so now we're going to step back a bit and we're going to look at some of the beautiful mathematical structures that underlie this area. We're going to talk about 2 Hilbert spaces. Hopefully you all know about Hilbert spaces. I guess you don't all know about 2 Hilbert spaces. So, here are some complex numbers you might have heard of. 1, 0, I, root 2 minus I, dot, dot, dot. There are lots more. Now, we don't normally talk about these guys, right, one by one, draw them out. We normally just refer to the complex numbers. Set. Okay. Now, complex numbers form Hilbert space. In fact, there are other finite dimensional Hilbert spaces. There are C, C2, C3, there are others. But often, it's useful, we've been hearing about a lot this week, not to worry about these vector spaces individually in an ad hoc way, but to group them into the category of Hilbert spaces. And work with this category itself as an algebraic structure. Now maybe you can see where this is going. There are other categories of interest if you want to model the behavior of quantum systems. Hilb is the sort of canonical one, but there are others that we could call Hilb2, Hilb3, and so on. But it's no good just studying these in an ad hoc way. Okay, boom! I should put a sound effect. We group them all together into the two category of two Hilbert spaces. Now the fantastic thing about this subject is that it never stops. Okay. But this level, the two category two Hilbert spaces, is very well understood. It's used all the time by all sorts of people in physics, in mathematics, in representation theory. And it's this piece that we're going to really understand in this lecture and see what it's used for, see what its properties are. How you go beyond this is a very interesting question. There's still a lot is unknown. We don't know. There definitely ought to be such a thing called 3-Hilb, which is a 3 category. And you could probably write down its definition, but then very little is known about its properties. So what is this thing, the two category of two Hilbert spaces? Well, what is really a two Hilbert space? Well, the abstract theory was developed by John Bayes. He was the one who really coined this term two Hilbert space and really encouraged people to think of it as a categorification of the notion of Hilbert space. So I'm going to have some mathematical definitions on this slide, just to warn you about. So, first of all, what is a dagger category? Well, we've seen that before. It's a category equipped with a contravariant involutive endofunctor, right, the dagger symbol, which is the identity of objects. So that just says for any morphism f from A to B, there's a new morphism f dagger from B to A, and that f dagger dagger equals f. Okay. Now what's a Hilb enriched category? Well, that's just a category such that for all pairs of objects A and B, the space Hom A, B is a Hilbert space. The composition is linear. By the way, throughout this whole talk, all my Hilbert spaces are finite dimensional. I don't always say that. Having said that, all this stuff can also be done more generally, including infinite dimensional Hilbert spaces, but I don't need that for this talk.
Does
that's
that
what
something like
enriched
infinity
categories.
Hilbert spaces?
Sorry?
Infinity Hilbert spaces.
Well, this 2 here doesn't refer to the dimension of the
No,
Hilbert
but means
space.
can you put an infinity there?
I don't know, Bob. You go and work it out. Sure, you can do that. Question is, what the hell is it useful for? We don't. Okay, now what's an H star category? We get it. Now, if you've got a Hilbert-enriched category, which is also a dagger category, you can put this very interesting compatibility relation on morphisms. Suppose we've got FGH, which are actually not all composable in line, but composable in the following sense: that F is composable with G, and the F composed with G is in the same Hom set as H. Let's draw what I mean. Simple A, B, C, F, G, H. So suppose F, G, and H are arranged like this for A, B, C, some arbitrary objects. Then F, G, and H are both members of this Hom set, A to C. So we can certainly take their inner product with each other, because our Hom spaces are Hilbert spaces. So we have an inner product of elements. So there's that inner product. But we could also do some other things. We could take the inner product of H composed with G dagger with F, third thing I've written. Or we could take the inner product of F dagger with H with G. And the H star axiom is that all these three inner products are the same. So it's a very natural compatibility condition between Hilbert enrichment and Dagger category structure. Yeah.
Why there should be more of those? Why without the H-tag ones and stuff? Are they more?
You can generate lots of identities just from this, but this is the definition of an H-star. It's not a theorem, so you can't argue it.
What's not very symmetric?
Well, so, okay. So what is a 2 Hilbert space? It's an abelian H-star category. So what's going on here? Why should we care about this? Well, because of this nice, firstly because of this nice theorem, every finite dimensional 2 Hilbert space, I haven't defined what finite dimensional means, but I haven't got time to do that sort of thing, is equivalent to Hilb to the n for some natural number n. So Hilb to the n just means the Cartesian product of categories. So Hilb squared would be Hilb times Hilb. A category whose object pairs of Hilbert spaces and whose morphisms are pairs of linear maps. Now, John Bay has emphasised that a 2 Hilbert space is a categorification of the concept of a Hilbert space. So let's see why that is. Well, a Hilbert space is a set. A 2 Hilbert space is a category, for starters. Given any 2 elements of a Hilbert space, I can take their inner product. It's a complex number. Here, given any 2 objects of a 2 Hilbert space, I can take their inner product in a sense, and the result is a Hilbert space, not a complex number. So everything's going up one level according to that initial hierarchy of all those bubbles that I showed you. And a Hilbert space is not only a vector space, it's got a norm and it's complete under that norm. And also for a 2 Hilbert space we impose completeness requirements. Yes?
I missed the definition. What is an abelian H-star?
Well, the notion of being an abelian category, that's a standard concept in category
okay.
theory.
So you mean an H-star category which is also an abelian?
Yes.
Nothing to do with being
Sorry, no.
No, an abelian.
Sorry, so I should have said that, yes. So being an abelian category is a standard notion of category theory that I didn't even say what that was. Sorry about that, if you haven't seen that.
You see what it is?
It's a good completeness. Oh, it's a little bit long. You say you want to be complete and co-complete, and you want some good preservation under pullback or something. I've got stage fright slightly. Well, this is what Wikipedia's for. Anyway, so this is the definition of the 2 Hilbert space. All the parts of the definition are somehow analogous. They're somehow categorifications of the ordinary Hilbert space notions, and we prove a theorem like this at the end, just as we do for Hilbert spaces in finite dimensions. Right? Every finite dimensional Hilbert spaces is isomorphic to the Hilbert space C to the n, for some natural number n. So the same is true here. Right? Hilbert spaces finite dimensionally characterized just by their dimension. Same is true for 2 Hilbert spaces. Always as nicely as one can possibly hope. So what is 2 Hilbert? It's a 2 category. It's symmetric monoidal 2 category. I've got time to tell you what that means, I'm afraid. So it's built in the following way. 0 cells objects are finite dimensional 2 Hilbert spaces, as we just defined. 1 cells are linear functors. So 2 Hilbert spaces are categories, so 1 cells are functors between them, but we want them to be linear. Now 2 Hilbert spaces, we can add morphisms with the 2 Hilbert spaces because the Hom sets are Hilbert spaces, so we can ask for this linearity property of the functor. So that's what 1 cells are, 2 cells are natural transformations. Note again, this is analogous to how we build the symmetric monoidal 1 category Hill, where we say 0 cells are finite dimensional Hilbert spaces, and 1 cells are linear functions. Right? It's all completely analogous, it's just a categorification of the theory. Now, this symmetric monoidal 2 category is extremely standard structure. I cannot impress on you the degree to which, if you hang out in a representation theory research group in some maths department anywhere around the world, this is just the sort of thing that they're working on. This is higher representation theory, but it's really what all the cool kids are doing. So we've got some mathematicians here, right, Nils? You agree? This is a very unremarkable structure nowadays, right? In certain circles. And what I'm saying is that we can use it in quantum computing. It's a nice thing. Now, let's get a bit of a better handle on this 2 category. There's a classification theorem that says these finite dimensional 2 Hilbert spaces are just n-fold copies of the category of Hilbert spaces. Right? So it makes it a lot easier to understand. Simplify the description of our zero cells. But then, of course, all we need to remember is this natural number here to characterize the zero cell we're talking about. And then, in fact, we can redefine the whole two category in a much more straightforward elementary way. Zero cells are natural numbers. One cells are matrices, Hilbert spaces, in the sense that if we've got the natural number n and the natural number m, zero cells, then a morphism is an m by n matrix Hilbert spaces, and two cells are matrices of linear maps. So if I've got some other such thing, then a two cell from here to here constitutes a linear map from this Hilbert space to this Hilbert space, and another linear map from this Hilbert space to this Hilbert space, another linear map from this Hilbert space to this Hilbert space, and so on. So it's just a component-wise family of linear maps. So I could have said this slightly differently, because of course our Hilbert spaces here are finite dimensional. They're also characterized by natural numbers up to isomorphism. So I could have said zero cells are natural numbers, one cells are matrices of natural numbers, two cells are matrices of complex numbers. So what we take away from this is that there is a matrix calculus, just as for ordinary finite dimensional spaces. In quantum information, ordinarily, we like to work with matrices, take their tensor products, and so on. And we can do exactly the same thing here. Everything just gets a little bit combinatorially more sophisticated because the basic entities are matrices of complex numbers. Matrices of complex numbers.
So when you multiply these matrices, you just tensor the...
So there are three ways that we can compose these matrices, because this is symmetric in one of the two categories. So we can compose them as two cells, vertical composition in this picture, in which case we just component-wise perform ordinary matrix multiplication. We can do one-cell composition, where what we do is basically generalized tensor product operation on the matrices. And the whole two category is itself got a symmetric monoidal structure, which is even another way to compose our two cells, which is a bit less easy to give an instant complete. Okay, here's a quote from Schrödinger, who of course put forward the wave function approach to quantum theory, and was, at least initially, unimpressed by the matrix calculus approach. I knew of matrix mechanics, but I felt discouraged by the methods, which are a bit difficult to me. I've used in square brackets an ellipsis here to make Schrödinger look as sort of pathetic as possible. Apologized. I know, Schrödinger, it's so hard, isn't it? Is it the first row multiplied by the first column, or the first column? Just give up now. It's too hard. So that wasn't really what he was talking about. That was the difficulty that he had in mind, right? But the point I want to impress is really, I mean, what many physicists say when I tell them about this, they say, well, obviously I believe in Hilbert spaces. Obviously I believe in Hilbert spaces. But two Hilbert spaces, come on, that's just ridiculous abstraction, right? Is that really what Schrödinger was saying 100 years ago, one level down the hierarchy? He was very happy with the notion of amplitudes, right? You do a measurement, some sort of amplitude. Okay? But organising these amplitudes into matrices, come on, that's ridiculous level of abstraction. That isn't some general way to do quantum theory, that's just writing down a load of amplitude. This is a ridiculous approach. You should use wave functions instead. Turns out it was completely. So, why should we care about two Hilbert spaces? Why should it be the case that these are interesting structures that have anything to say about quantum computation? We can motivate this quite clearly, I think. So what happens after we perform an n-outcome measurement in ordinary quantum information? Well, what happens is that the whole scenario branches, right? Not in some woolly, multiple universe kind of way, right? Although I have to be rather sympathetic to that way of describing things. Just in a practical, completely practical sense. If we wanted to write down a complete set of instructions for how to perform a quantum algorithm, and that algorithm involves certain quantum measurements, such that the results of those measurements are going to affect what you do in the future, that's a so-called adaptive quantum algorithm, which is all over the place, then what you have to do is your description of your procedure, which you're going to give to your experiment and event list, has got to branch, right? Whenever there's a measurement, you've got to tell them what to do, depending on what the result of the measurement is. So, how do we model state space of our system after after an n outcome measurement? Well, simply with a family of n Hilbert spaces, right? And which Hilbert space we're in will depend on the outcome that we got, because we're going to do n completely different things perhaps afterwards. And what are the future dynamics? Well, just described by a family of n linear maps, unitary maps probably, at least until such a time as in one of those n scenarios we then go and do a further measurement, and it branches even further. So what's a natural algebraic structure to use to describe families of n-fold families of Hilbert spaces equipped with n-fold families of linear maps? Well, just the n-fold Cartesian product of the category of Hilbert spaces, obviously. Right? It's a very natural structure. But these are exactly the objects. These are exactly the two Hilbert spaces. Exactly these categories, no more and no less. These are all that two Hilbert spaces are. So they seem really very reasonable objects that in any formal description of a quantum procedure we might like to use. Okay. So common here for Bart. This is the Eilenberg-Moore category for this monad. The monad have taken the tensor product with the n-dimensional commutative algebra. So that's a monad on the category of Hilbert spaces, and this Eilenberg-Moore category is going to be held here. And that's something that Bart has used in his work on co-algebraic methods for computing, so really he's been working with this category, or maybe he hasn't called it a two-Hilbert space or cared that it's a two-Hilbert space. So Bob Cooker and Pavlovich also did very similar things long before. I don't know, when was this, Bob? 2008 or 2006? So they said, okay, we've got this branching structure that's naturally present in any description of the quantum protocol. How can we describe it? Well, they said, whenever we do a measurement, that's a dagger module from a classical structure. A classical structure is this commutative Frobenius algebra object, and it's acting on a Hilbert space as a module. And that module structure is exactly giving us this decomposition of our Hilbert space into a family of n subspaces. And they said dynamics, module polymorphisms. So that works perfectly, it's all completely correct. So you can say, fantastic, what do I get? If I look at classical structures, dagger bimodules, and their homomorphisms, then you get a two category, and you just get two Hill. So this is not some radically new approach to describing how quantum systems organize themselves. It's just what people have always been doing, and it's the only thing you could ever do. Right? Simply as the case that these structures organize themselves in a two category, we may as well recognize that fact. So what do we gain from working with two Hill, as opposed to, say, working with classical structures, bimodules, and homomorphisms directly in the category of Hilbert spaces, for example, or some other concrete thing? Well, first of all, we can forget all those axioms. We can totally forget the classical structure axiom, because the classical structures are now just objects in our two category. So we forget all these axioms, Frobenius algebra, blah, blah, blah. We just say we have an object. We forget all the bimodule axioms, which there are several. We just say we have a one cell. We forget the bimodule homomorphism axiom. We just say we have a two cell. No axioms anymore. All the equations are completely gone, as long as we started in the right two category. Luckily, that two category is very easy to define, as we'll see. Objects are natural numbers, morphisms are matrices of natural numbers, two morphisms are matrices of matrices of complex numbers. We get new avenues to generalization. We can now, given any two category, interpret as a sort of toy theory of quantum mechanics, where not only do we get quantum systems interacting, but we also get measurement. We also get this splitting of the state space built into the categorical structure in the way that we'll see. We also open up deep connections to all these fantastic areas in topology, string theory, and so on, where representation theory, where these higher algebraic structures are being used, exactly the same higher algebraic structures, two Hill and so on, actually being used in very similar ways to do very similar things. So we start speaking the same language with these people. Of course, the most important thing is that it's great fun mathematics. That's Bob will certainly agree with that. So now we're going to think a little bit on a different tangent now. We're going to think about basic properties of copying, comparing, and deleting classical information. So forget all that rubbish we were talking about before. So you want to build a black box, three black boxes, machines, one machine that will copy data. So here's our copying machine. One thing comes in, two things come out. And a deleting machine, where one thing goes in, nothing comes out. And a comparing machine. This comparing machine is a little bit less straightforward, so I'll describe what it does. It's quite simple. Two things come in. The machine looks at them and says, are they the same? If they are the same, then that same thing comes out. Okay? If they're different, then the machine fails and explodes, or a red light goes off, or something like that. So this machine is asserting that these two inputs are identical, and then repeating that input, that unique input in the output line. Another interpretation is that this vertex is post-selecting on the case of those two inputs. Okay, now you can think, well, suppose I have those machines, what properties would I want them to have to really believe that they are doing their jobs properly, copying, deleting, comparing? You can write some things down. This looks a lot like associativity. It's perfectly reasonable. If you make a copy, the first copy, that should be the same as making a copy. The second copy, if you make a copy and delete the first copy, it should be the same as doing nothing. If you make a copy and swap the copies, that should be the same as making a copy. And there's a slightly more interesting one. If you start with two pieces of data, you copy the first, and then you assert, you post-select, you force that copy to be the same as the second copy, as the second piece of information rather, then what have you done? Well, if this piece of information is A, B here, then here we'll have A, B, and here this asserts that those two inputs are the same. So at the end we just get A is spat out with the requirement, constraint that B is equal to A. So overall, the input is AB, and the output is AA, with additionally the constraint that A is in fact equal to B, post-selection. And the right-hand side has exactly the same output. So we also expect those to be equal. Now, how can we remember which equations ought to be equal? How can we list them? How can we classify them? Well, we can use a different notation. We can just fatten up our little diagrams, pretend that they're surfaces. Because the things that will be true with respect to our copying and deleting, comparing procedures and so on, are just exactly the things that are true for surfaces, no less. So it's a useful notation. Just as we've seen in earlier talks, how the string diagram notation is a useful notation for the preparation of an entangled pair of systems. That was some one-dimensional topology, getting into the description of informatic properties of systems. Now we've got some two-dimensional topology, also getting into the game in a very different way. Nothing here about correlation or anything. Okay. So if we wanted to make use of this fundamental axiom, we've seen several times before this week, what we do is we say, we assert that working in a monoidal category where this axiom is always satisfied. Okay? So what do we say if we want all these axioms to be satisfied? Well, we have to be able to draw surfaces for starters. So we better be in a 2 category. In fact, here we really want to draw cylinders. In a cylinder, you've got a front surface and a back surface on top of each other. That's an extra direction of composition you need to. Really, you need to be in a monoidal 2 category when you draw these diagrams. And we simply, because we've seen, of course, before in the other lecture that the graphical calculus for a 2 category involves these regions. So we can draw these regions in a monoidal category, we can overlap them, and we can draw these cylinders, we can draw all these surfaces. And then we simply insist that these surfaces behave, these diagrams behave, just like ordinary topological surfaces. And if we insist on that to be the case, then we're guaranteed that our surfaces will indeed correctly model the way that classical information is copied, compared, deleted, and so forth. Okay, so now we're going to suppose we're in such a setting. We've got the ability to describe quantum systems or local systems, whatever you want to call it, perhaps equipped with entanglement. And we've also got the ability to describe these classical systems described by these surfaces. Given all these features, we can describe now interactions between these 2 types of structure. So the first thing we can do is we can say perhaps we've got some local system, quantum system. We can transform it into a non-local system, into a system that lives on the surface, into a classical system. So we interpreted the behavior of these surfaces as mimicking the behavior of classical information. Now this is what a measurement is. It's a way to turn quantum information into classical information. So we'll simply allow ourselves to add this. We'll add this as a 2-cell in our symmetric monoidal 2 category. Perfectly good thing we can do, and we'll interpret it as a measurement if we're thinking quantum mechanics. We could also do the opposite procedure. We can take some classical information and we can convert it into quantum information. That's what happens if, for example, I don't know, I tell Peter Selinger, I say, prepare me a qubit in state 0. And he does it, and he gives me. I could have said, prepare me a qubit in state 1. I don't. That's Peter, right? P for Peter is a process that turns classical information into quantum information. Now, third interesting way that a line and a surface can interact is like this, a little bit turned on its side. This is a controlled operation. The idea here is that something is happening to this quantum system. And exactly what is happening depends on the value of classical information that's living on this surface, it's encoded on this surface. These are the 3 basic ways that surfaces and lines can interact, and these are the interpretations, relatively natural I think, when I'm loading on top of these vertices. Now you don't have to believe these interpretations, but you have to believe the theorems that are coming later about these structures, and you'll struggle to understand why those theorems will be true unless you also buy into these interpretations. Now, crucially, we require all these 2 cells to be unitary 2 cells. Philosophically, that is because all processes in physics and computer science are arguably, modulo those discussions we had on the first slide, reversible at a fundamental level. Classical computer science, we really predict is reversible. Quantum computer science, it's at least arguable that all processes, even measurement processes, are reversible. In particular, these measurement and preparation processes, they aren't arbitrary unrelated processes. We would want them to be inverse to each other. Now let's think about that for a little minute. So let's think about that a little bit. So one way round it says, if Peter prepares me, if I give Peter some classical information, he encodes that into a quantum state, and then I measure that piece of classical information, overall I should just get the identity. And that's indeed what happens, because if you encode some classical information into an orthonormal basis state of a system, and then you measure the system in that basis, well, you'll just get the original piece of information back. So that's correct. But also we're saying if you chain these in the opposite direction, you get the identity. That is, if you have a quantum system, you perform a measurement, and then afterwards you perform a preparation to re-encode that classical data back into a quantum system. You get the identity. It's as if the measurement has been reversed. That's exactly what this is saying. Now you might think that that contradicts our experience in quantum theory, which is that if you perform a non-demolition measurement on a system, and then you take your classical result, or rather, sorry, if you perform a demolition measurement on a system, so you effectively consume your quantum system, turn it into classical information, and then you attempt to re-encode quantum state, you get a system that's definitely in the basis state. The wave function has been crushed. How could it ever be the identity? The point is that the equation that we assert here is that if you measure and then you prepare, you get the identity. Now, what is the interpretation of this surface? This surface is the future light cone, if you like, that carries all the information of that measurement result. Okay? So what we're saying here is we do the measurement, we collect all those particles which have emerged from our measurement site and which encode the result of that measurement, and we then push them back together and we reverse the original measurement interaction. If we do that, we get the identity. That's something that I think all physicists and quantum computer scientists. Because what happens in the lab when we do a measurement and then try and reverse it is something completely different. We do our measurement, we have the future light cone of all the particles, photons coming out of our light source, out of our incandescent bulb in our ceiling of our lab. They're bouncing off the notebook where we've written the answer, the result of the measurement. They're flying out the window at the speed of light, as photons like to do. Right? So here they are. They're flying away. All these bloody photons. Right? They're carrying away the measurement result.
You say you had
All
a
sorts of
demolition.
dimensions. What's that?
You said you had a demolition measurement.
Yes, I have demolition measurement, so my quantum system is gone. I'm left with classical information. This classical information is escaping in a way that's almost impossible to prevent in every direction. These are all classical systems because they're surfaces. I now take one piece of classical information and I re-encode it back into a quantum system. Well, that doesn't equal the identity, and it's got nothing to do with this axiom. The point is that this formalism allows us to describe the entire locus of the classical information that's emerged from quantum measurement. What happens in general is we cannot control what then happens to that quantum measurement in a real lab setting. But in certain settings, and indeed these experiments have been done, you can go to perform a quantum measurement, but then if you reverse that process at a very early stage, so say just before the photomultiplier has managed to magnify this quantum path of a single electron into a huge avalanche of 10 to the 20 photons or something, if you can reverse that at a very early stage, then you do get this so-called quantum erasure experience. It's all about whether you can control the information that results from the measurement process. Now, let's go back to our heuristic back-of-the-envelope description of quantum teleportation. This is the picture that we drew. Well, the left-hand side also, what's the right-hand side? The point is it's no good doing these things if we're just making it up as we go along. Right? It's no good if we prepare any old entangled state that we like. It's no good if we then perform some arbitrary quantum measurements. It's certainly no good if we perform some arbitrary correction step, right? It's got to be the right stuff. It's all got to work together. It's got to be a plan. That is, overall, these three procedures have to satisfy an equation. This is the equation. The equation says that if you do these things, the initial quantum state is transported over into this final position here. And this classical information that's broadcast is completely uncorrelated to that quantum system. So here it's spatially separated, right? Those parts of the diagram are not connected. Now, all of these aspects of this diagram are things that we understand in terms of our two categorical calculus. So we can rewrite this diagram in this way. This is a heuristic diagram written on the back of a envelope or napkin or whatever it is. Not that where you write something affects how rigorous it is, but this is a diagram which you could also write on the back of a napkin, which is completely rigorous. It doesn't mean it's correct or it's got anything to do with anything, but at least this is mathematics. On the left-hand side, we have a composite two-cell in the monoidal two. On the right-hand side, similar. This is an equation saying that these two cells are equal. Then we prove the theorem, which is that solutions of this equation in the two category of two Hilbert spaces correspond exactly to actual implementations of quantum teleportation. That's the point of all of this. So let's again understand how we interpret a whole picture like this. Whenever we see a line, thin line, we interpret that as a quantum system. Whenever we see a region, we interpret that as encoding or carrying classical information. So here, this classical information is the result of this measurement. Here, this classical information is just uniform random information. Uniformly distributed over all the possible values of the table. Now let's look more closely at all the different processes here. Every single time anything interesting happens, either on the left and right end of these diagrams, it represents some physical process which is taking place. Here we've got this bent piece of wire, that's creation of an entangled state. Here we've got this transformation of quantum systems into a classical system, that's our quantum measurement, that's our measurement result, this is our control operation. Okay. So why should this theorem be true? And why should we really interpret all these things in this way? Why should we interpret a vertex of this type as a control operation? Why should we interpret a vertex of this type as quantum measurement? Well, because, firstly, this theorem is true. Secondly, in the process of proving this theorem, that's how the construction goes. If you've got an implementation of quantum teleportation, and you want to use it to build a solution to this equation, then the instructions for how to perform the measurement, you use them to decide what two-cell, how to define this two-cell n. And the instructions written down that the experimentalist has given you as to how he's going to perform the controlled operation, you use them to define this 2 cell here. Right? So here's a particular example, just to show you how totally concrete and unscary all of this stuff is. 2 cells in the 2 category 2 Hilbert spaces, they're matrices of complex numbers. So for all these non-trivial things where anything's happening, I need to give you a matrix of matrices of complex numbers. So here they are. They're totally simple, straightforward things, and in fact they comprise exactly the data that's obviously needed to communicate how to carry out quantum teleportation in the following way. So experimentally says, this is how I perform quantum teleportation, say for a qubit. First of all, I create an entangled state. What state do you create? Oh, I create the Bell state. Well, here it is, 1001. It's an element of the Hilbert space of 2 qubits. So what is this whole entity? It's a 1×1 matrix whose unique entry is a 4×1 matrix that defines the Bell state. Then, says the experimentalist, I do a measurement. I do that in the Bell basis. Oh, that's interesting. Say, can you please tell me the 4 vectors that comprise the Bell basis? Yes, of course. They are 1, 1, 0, 0. Sorry, we're reading across. They're 1, 0, 0, 1, 1, 0, 0, minus 1, 0, 1, 1, 0, 0, 1, minus 1, 0, divided by square root of 2. So what I put in here is a 1×1 matrix with single entry, which is a 4×4 matrix, which is the unitary operator that rotates the Bell basis into the computational basis. That's the rule I'm applying to construct this solution equation. Finally, the experimentalist says, in the correction step, depending on the measurement result, I either do the identity, or I do this 2×2 matrix, or I do this 2×2 matrix, or I do this 2×2 matrix. And so, the value that I assign for C is a single 4×1 matrix whose entries are 2×2 unitary matrices, which are just exactly the correction steps. So the proof of this theorem is just completely immediate and just by construction. Yes?
In case of the measurement, instead of a 4×4 matrix, I would have expected that to be a column vector of 4 row vectors. Why is it 4×4?
Good question. So the reason that it's like that is that whenever we're in the uncoloured, whenever we're in the uncoloured fragment of this diagrammatic calculus, just means that we're working just in the category of Hilbert spaces, actually. Just the scalars of the 2 Hilbert spaces. So let's look at M. Its input is H tensor H, and its output is something that we're drawing like this. Okay? It's got some 2-dimensional structure, some surface, but all we care about is it's a big fat wire. Overall, it's a 1-morphism from Hilb 1 to Hilb 1. So it's a linear functor from the category of Hilbert spaces to the category of Hilbert spaces. So it's just a Hilbert space. So what is M? It's just something that lives in this uncoloured fragment. So this is just some Hilbert space H prime, and M is just a linear map from H tensor H to H prime. So there's only one thing we need to give, a single linear map. So that's why it's a 1×1 matrix. In general, if you've got, I don't know, some 2-cell sigma here, and this is Hilb N, and this is Hilb M, then sigma will be an N by M family of linear maps. So in this case, it's clearly 1×1 family. Okay, now, what else? We can apply this topological language to lots of procedures in lots of phenomena in quantum information. Another interesting phenomenon is dense coding. The picture we draw for that is very different, because the steps that we carry out for quantum dense coding are very different. So what is quantum dense coding? Well, we can read it off from this topological procedure. It goes like this. We start with some classical information, totally different from quantum teleportation, where we started with some quantum information. We started with some classical information. We prepare an entangled state. We then perform some unitary procedure to this entangled state, such that the procedure we prepare, well, it depends on the value of this classical information. And then, at a later stage, we take both of these systems, we perform bipartite measurement, producing some classical information. The result of doing all of these things is that this initial piece of classical information is simply copied. In particular, the value of classical information living on this part of the surface is identical to the value of classical information that was in here. So why is this so interesting? Like quantum teleportation, this is another procedure that's obviously impossible if you apply naive classical expectations of how information can move around. Quantum information can be very surprising. The reason this is so surprising, if you haven't seen it before, is that it describes essentially the transmission of data, the transmission of 2n bits through 2n classical bits through a channel with classical capacity which is only n bits. Seems completely impossible. So why is that? Why is this such a paradoxical situation? Well, all of these procedures are invertible. In fact, they're unitary. C and n in particular are unitary. So, if the overall effect is to copy this procedure, then certainly this final piece of classical information must be of the same size as this initial piece of classical information. Let's say n squared is the dimension of the state space. But this procedure m is invertible. So whatever this item here is here, it has to be the product of two other integers. But this integer must be the same as this integer, must be the same as this integer because these are maximally entangled. So this has to be a square, it must be the square of something, let's say n. So then this is the size of the channel, the quantum channel which passes from left to right, just of size n, dimension n. Yet overall it's n squared is the dimension of the information which can support it. That's why it's paradoxical. Again, theorem, solutions of this equation in 2-Hill correspond exactly to implementations of quantum dense coding. So this isn't just a load of pretty pictures, it actually does what it says on the tin. So then another nice fact, something that's well known, is that if you can perform quantum dense coding, that's equivalent to being able to perform quantum teleportation for the following reason. Simply the case that these three ingredients, M, C, and this entangled state, these were all we needed to use to do quantum teleportation. M, C, the entangled state. We're just chaining them together in a different order. So it's well known that if, and in fact, not only are they the same list of ingredients, in fact, if your three ingredients, M, C, and the entangled state, are correct for performing dense coding, they'll also be correct for performing quantum teleportation and vice versa.
This is true in Hill, but it's not necessarily true in another category.
Well, it turns out that it is.
No, it's not.
Well, in this setup it is, because you can deform this equation topologically and obtain this equation. So in this setup, you can show that logically, at the level of logical structures, nothing to do with actual implementation, say in 2-Hill, this equation, quantum teleportation equation, is equivalent to the dense coding equation. So we have
the same type.
well, that's fine. This is an equation between certain algebraic structures in some symmetric model 2 category. This is another equation you can show just by performing topological deformation, which could change the overall type, by the way. Right, something we're familiar with in quantum mechanics. If we've got some system phi, we can do some morphism phi, we can do topological deformation and get something of a different type, right? Process. So it's just by generalizations of this process we can transform each equation into the other. So that's a logical proof of the equivalence between quantum teleportations.
So how do you do this stuff?
Just to the right-hand side of both equations.
You want me to do it? Okay, so it's a little bit, I mean, it's quite a lot of steps. I can just do it. It's not a secret, I mean, I can show you. It would probably take me 10-15 minutes to write it all. It's like 7 or 8 steps.
If you do this in your categories, you get different equations for validity of the two, which in the other space imply each other, but in general don't seem to.
Well, in this setting, in this, if you require all this topological structure, then do, because it's there. So if you have some model of some toy model of quantum theory, in which quantum teleportation and let's go are not equivalent, then it won't be well described by this geometrical logic.
So the right-hand side of that equation is disconnected. The right-hand side of the other equation is not.
Right. So it's right. So that's true. It's not mere topological deformation. You've also got to do some algebraic rewriting. A certain. That's true. So it's not just mere topological deformation of the left and right hand side. You've got to do things like, one of our axioms was the fact that this C was unitary. Okay? So if we hit with C inverse on both sides, we'll have a completely equivalent equation, in now which both sides are connected. They'll clearly be completely equivalent. So we have to use procedures like that and do some more topological deformation. So I must admit this is a couple of years ago and I can't remember exactly how I got it, but I'm happy to show you that. And that's it. Okay, thanks.
Questions?
It would take 15 minutes to do it. You finished 15 minutes early.
No.
You
We didn't finish 15 minutes early.
Yeah,
But
I take it back.
you can do it fast. But I don't think this is easy if you can do it. Because
Well, I just said it's not like 2 lines, it's like
I actually still don't believe it, but okay.
So you're saying that your measurements are perfectly invariable. It seems to be saying that your measurement is capturing the amplitude of every outcome of the measurement at the same time.
Yep.
Isn't that contradiction with what we usually understand what the measurement to be? It seems like if you want to live in many worlds and you have a wave function universe, that might be right.
Well, this is nothing to do with many worlds, firstly. I mean, as I sort of set things up a long time ago, the idea is simply that if you want to describe what happens after a quantum measurement has taken place, you then have n copies of the categorical spaces lying around. And that's a two-logical space. And this is the logical structure of two-logical spaces. All of this you could do, say, in terms of classical structures, modules and modular homomorphisms. Because of this thing, 2-Hill is just equivalent to classical structures by modules and homomorphisms. Translate all into that language, it would just look very
Could you
different.
do a 2 CPM category?
Yes, you could.
Because
That's
that
what
would
our,
fix all the problems.
well, that's
But
what our
I agree
QPL
with Ross that this is just not something you want there. And 2 CPM would fix that.
What's not something that you want?
Well, that equation in the middle of the board there, which
Okay,
seems
so
to
when I
indicate
say
that you tomographically get good.
so when I say this here is a measurement, I mean it's a PVM. It's not a PVM, it's a PVM. This is a pure state. Does that answer your question, mate?
No.
So this is a pure state fragment of quantum information that we're doing, which is more sufficient to talk about quantum teleportation data itself. If you want to talk about the logical structure of procedures in which you necessarily perform PVMs, then you need to go to the mixed world. That's what we have this QPL.
No, but I mean, in the mixed world, this equation doesn't hold anymore. That's the whole point.
So you say
That's the
your
whole
measurement is
point.
basically post-selected, you're living in a post-selected world.
No. So this whole talk about pure
He
state
remembers amplitudes.
quantum information.
He remembers amplitude because he lives in Hilversberg and Leipzig.
So everything is still there.
I have 2 questions. One is, if the measurement in preparation or each other's inverses, then an object which you represent by a line and an object which you represent by a hose are isomorphic, so therefore why not 2 different objects at all?
They are non-equal isomorphic one cells.
I would say it makes exactly the
Yes,
same
but
mistake as Samson and I made in our first
Couldn't you
paper.
write everything as a hose then, right?
Um,
If they're isomorphic.
No, you couldn't, because it turns out that you could force yourself to pass to some equivalent, non-equivalent 2 category, but it would make life a lot, which would be more skeletal in some sense, right? But it wouldn't help you. It would make things a lot harder, because I mean we have things. This is a one cell example. This is another one cell, right? So we can compose them. This is a one cell composition, and the result of that composition is something that's very natural to write like this. Now this one cell is isomorphic to this one cell, but the point is, whenever you use such an isomorphism, that's something structural that means something that's happening. Right? You don't just replace this with this. That just messes up the type. It's important type information.
Okay.
Yeah. Yeah.
How do you represent quantum zero effect with this?
No idea.
Because the thing is, if you perform measurements in a quantum system, they state towards where you want.
I mean, this is just a funny language for ordinary pure state quantum theory. Anything you can do in pure state quantum theory, you can just write down.
Alright,
Yeah, I mean, if you want to do some funny chain of measurements that has some chemical property, then you can write it down. But unless that has some geometrical description, it won't necessarily look any nicer.
So, like when you showed your four equations, so Frobenius algebras,
Yep,
you left of course one out
yep, that's true.
for obvious reasons. Is there any way you know?
So I left out this one. This one doesn't hold. You don't impose this. So this is not one of the Frobenius equations. This is the special. Is this the equation you're talking about? Right. So I left out for obvious reasons, which doesn't hold.
Could
Either topologically or in this mathematical.
I would wonder whether one way or another trying to account for that one could actually fix the problem with the MT, which I don't think is a good solve.
The fact that this equation holds.
This is one which shouldn't hold.
So that's totally crucial that holds. It's the foundation of the entire thing. This does not say that you do a classical measurement and then a preparation, and it's if the wave function will never collapse. So that process is described by this picture. It's a completely different picture. This says if you do a quantum measurement and then all the physical systems in which the results of that measurement are encoded can somehow be captured and stopped from escaping and the measurement reversed, then you'll get the identity. But that's totally unobjectionable. There are papers on this phenomenon all the time. These quantum erasure papers, all this.
Pretty sure nobody go to physics. Nobody's going to buy this.
No, I think
It's a totally standard thing.
No,
It's totally wrong. It's a massive area.
these pictures are not the same as your pictures, right? Because in your pictures they are mixed states.
Sure. If you do a
Even
measurement,
classical states are pure.
this seems to indicate that you can do tomography from one measurement.
No, because you don't get information out.
There's no information.
Even
no
your
classical
picture
information
is,
state.
when you twin it, you know, you have the thing that looks like a rounding symbol. It's actually a shorthand for information escaping into the environment, right? So that would be more like the picture on the right hand.
But so that isn't really a measurement, and that you shouldn't think of this as a
That's not
measurement.
what you would call it.
Right. I mean, if you're modelling a quantum system, if you're modelling a quantum, if you're drawing a picture that's supposed to be modelling some real quantum procedure you do in a lab, like the teleportation equation, right, like this, you better not ever draw anything like that because that's totally unphysical.
Oh,
You never achieve this. We can draw things like this. That's totally fine, but we must never allow us to draw that. Well, in fact, because there's no point doing this. It's just
Am I right to say that this is actually not a measurement? M is something like half a measurement, and then if you stick it out,
if you like. Yeah. I mean,
Okay.
obviously.
because you wouldn't call that because this is not for a measurement. This would not be true.
Well, I think it's useful to call it a measurement. If you want to call this bigger thing a measurement instead, then
Did you say that this was something like letting my system interact with some quantum pointer or something and then putting the pointer state back in the system?
I would say this is like taking my quantum system and encoding its quantum state, taking my quantum system here and encoding its quantum state into an arbitrarily large family of extra systems, right? Which are all perfectly correlated with one another, and they're promised to all be perfectly correlated. Therefore, their total tensor product space, quotient by the restriction of this correlation, has the same dimension as this input system. Right? That's just what a measurement is, right? I mean, when we do this photomultiplier effect, we've got our little atom that we're measuring, and some quantum event happens. Say it releases a photon, or it doesn't release a photon. When it releases the photon, it hits the side wall of our photomultiplier tube. An electron comes out. 30 more photons escape. They release 30 more electrons. 10 to the 4 photons escape. All these photons are entangled with this atom now. The whole system is in a superposition of atom not decayed and photons not existing, and plus atom decayed and all these photons existing. Right? All these photons, this is what these lines are. Now, if you can manage to catch them all and push them all back, which is easier the sooner you get on with it, right? Then you can reverse this measurement, and that's exactly what these people do in these experimental papers. They have a procedure whereby they can halt the action of this photomultiplier, and they do it at earlier and earlier stages, and they find that if they can halt it at such an early stage, such that they can show that it's very likely that no photons escaped, then quantum coherence is maintained. And if they do it at such a time as seems that it's unlikely that they managed to reverse all those quantum effects, then it's not maintained. Just exactly so. So either they managed to do this, where they've collected all these photons and then transformed their state back, or they're in this situation where there's some lost, and that's exactly decoherence or no decoherence. It's just totally sort of bog standard, quantum theory. Okay, should we go and drink?
Okay, let's go drink.